Who wants to go through number A? Letter A. Letter A.
Are we not doing those?
Okay, last night you guys went over some moles. You learned what a mole is, what its units are, and what it's used for. And you should be able to do this, I think. So can someone volunteer for A? Or I'll call on someone. Yes.
Me or
Either one. One of you can do A, one of you can do B.
So mole mass of sodium hydrogen phosphate is 141.96361.
141.9 grams per mole. Did everyone get that answer?
Yes.
Roughly? Sure, yeah. I don't think you normally need that many decimal points, but what? Legible? Is this legible, guys?
It's good. It's good.
Yeah, exactly. It's better. They're saying it's better than yours. So,
Yeah.
sorry. Okay, part B. Part B.
I'm going again.
Or
I'll go.
sure.
Well, you got half a mole of sodium, right?
Half a mole of sodium?
Am I right? Am I wrong?
Yes, Annalise.
4 moles of sodium, 2 moles of hydrogen,
Oh.
8 moles of oxygen, and 2 moles of phosphorus.
Yeah, phosphorus. Yeah. So there's 2 moles of like sodium per each mole. And so if you have 2, you do 2 times 2, which is 4. See? Someone want to volunteer? Yes.
So basically you have to find the molar ratio, and then so you do 65 grams times 1 over your mole mass, which is 141.96, and then you multiply that all by Avogadro's number, which is 2.023 times 10 to the 23rd. You get 2.76.
Wait, what was the answer?
2.76.
2.76 times 10 to the what? Yes. Good point. Yes, it should be 2.8 because there are 2 sig figs. I can answer. Okay, part D. Any questions on that? No. Great. Part D. Yes.
So for part D, you got to do the same thing, except you have to multiply it by 4, and instead of 65 grams, 5 grams, which will give you 8 times 10 to the 22 oxygen atoms for 5 grams of sodium hydrogen phosphate.
So shaky. Okay. And that gives you what?
8 times 10 to the 22 oxygen atoms for the 5 grams of sodium hydrogen phosphate.
Is that what you said? Okay, cool. 8. Yes? Everyone agree? Fantastic. Times 4 is because there are 4 oxygens per mole of whatever this substance is. Yeah. Okay, great. Any other questions? Thank you. Okay, so notes. Yeah, so yesterday you went over some stuff with the mole, and today we have a few more terms about moles. And our first one is molar volume, and the definition is a space occupied A space occupied by 1 mole of a substance. Studio just froze. Your iPad just crashed. Let me pause it for it. Yes.
No.
Okay, Maggie said no. So can someone?
No,
So,
hold on. I just don't summarize.
okay, so molar volume is the space occupied by 1 mole of a substance, and it's applied to liquids and gases. Liters is or its units is liters per mole, and it's only this value of 22.4 liters per mole at standard temp and pressure, which is this value right here. Okay, so it sounds like you're not done yet, but we're just gonna move on. Can someone give me the first step of what to do? Yes, Leo. You multiply by 1 mole over 22.4 liters. So this cancels out the liters and we have moles. And then what do we do? Yes.
Calculate molar mass.
Okay, what is the molar mass? 16 grams per mole. That cancels and that gives us, yes, 8 liters, 8.0 liters. It's because I crossed it out. So
Okay, got it. I understand.
that gives us like 12 or something, right?
Oh my god.
Alright, I got it.
12?
5.7.
5.7
Or 12.
or 12. 5.7 grams. It's close enough. 5.7 grams. Okay. And so our other term for this lecture is molar volume, which is, I should type this. Molar volume is the constant. Can I move the keyboard? I can. Concentration of a substance in a solution. Concentration of a substance in a solution. Okay. Yeah, that's unlike molar volume, its units is moles per liter. And since we're going to use this a lot, we actually abbreviate this just to capital M. And it's applied only to liquid samples. Yes? Yes. Okay, so another practice problem. Go, do it. 1 minute. Thank you for bringing that up. Good reminder. Thank you. A standard solution, if you see this in a problem, this just means that like, you know, the concentration. So in an AP test, if they give you some experimental design and it's like, when you work with acids and bases later on, they're like, how much of an acid you need to cancel out this base? And they say of a standard solution, it means you know what the concentration is. Yeah. Practice problem.
The 6.022.
And you
Cancel out the moles.
6. So we're saying we start with 0.047 molarity.
Yeah.
Mhm.
The Avo number.
And so
Isn't it over 2 liters? Isn't it over? Yeah.
yes. So it's not just over 2 liters.
Yeah, it's in the small part.
Yeah. So we multiply this later, but we need to cancel out all the units first. It's like, so to cancel out the liters, we have to multiply by 2 liters. And this lets us cancel out the liters. And then we cancel out the moles by, someone shout it out. Molar mass. If we use molar mass, then we're left in grams, right? We don't want to use grams.
Oh, you want.
Your molecules, right?
Wait.
Oh, what do you mean? Okay, hold up. No. I actually know how to do this. I swear to God. Wait, you said you want avocado.
So I got it. What are the units for Avogadro's number? Molecules.
Oh, it's like this happy little chart thing that you printed for us yesterday. The little flower.
Yeah, and then this cancels out, and we're just left with molecules. And so that is.
I thought it was things.
What about the molar?
You're right. It could be things, but in this case, we're looking at molecules, so we want to have molecules.
The molar mass, because this could apply to any element.
What do you mean?
Because like, there's nothing about fluorine.
You only use molar mass if you're converting from grams to moles, but unless you're otherwise asked to convert to go to grams, you don't want to go to grams unless you have to. So either it's given to you as a starting in grams, or you're asked to report in grams. Otherwise, you don't use molar mass.
Yeah. All of
Grams is
these.
super unreliable.
And that gives us a number that is 5.61. Okay. 166. So 6 times 10 to the Avogadro's number is like it's the amount of like hydrogen atoms that takes to make 1 gram, and so it's just like the unit that we use for everything else.
They define it as the number based on like how many AMU kilograms.
Yeah.
Straight from to grams.
Yeah. So we can do the next one together. Yes, Annalise, question. Ions. You're right. Ions. Is there a difference? Molecules are more than 1 ion. Ions are like any atom that's charged on its own. Well, they can be molecules too, but yeah, you'll learn more about that later. Anyways, moving on. Isn't it?
No, it have to be ions. No, they're like the same.
Yes,
They're like the
yes.
same.
Ions per mole. Okay. Any other questions? No, great, fantastic. Moving on. Let's say I want to make a 30 milliliter sample of 2 molarity salty water NaCl. How much salt should I dissolve in 30 milliliters of water? So, so we want to have 2. So we start off with our given constants, which is 2 molarity, which is moles per liter. And we multiply by 0.03 liters to cancel out the liters. And that gives us moles, which is 0.06 moles of NaC. Yes. It's 30, so we multiply by 10. So there's only 1 0.
2 moles of NaCl
2 moles.
in a unit.
Where?
Then 2 moles over liter should next be 2 moles NaCl.
We're given, well, we want to get 2 molarity, like the capital M is molarity, and that's moles per liter.
Yeah, but it would be 2 moles NaCl, not just 2
Yeah. You're right. NaCl, you're right. 2 moles of NaCl.
Yeah.
Technically, it is a unit, but
We do often think of substances like units because sometimes what we'll start doing is we'll convert between substances as well as the units themselves. So it's a good practice to start tracking, especially if you're going from talking about a compound to individual ions or talking about. So for example, the problem above, you might have talked about. Well, no, those are all just ions. So, but it is a good practice indeed. Also, you need to finish this up and move on to composition analysis.
okay. And so we have 0.06 moles. And to get that into like solid salt, we need the molar mass, right? Grams over moles. And that's 58 grams per mole. And that gets us 3.48, which truncates to 3 grams of NaCl. Truncates. All good? Okay. Moving on to compositional analysis. So compositional analysis and empirical formula. Mass spectrometry to identify and quantify the percent composition of a compound by breaking it into fragments and measuring the percent contribution of each type. The percent composition. I just read the definition. So this is used when we don't know what the formula for like a compound is, and we need to figure out what it is. And so obviously, if you're given the chemical formula, then we don't need to do this whole process that I'm about to teach you about. But yeah. So the first step. Wait, do you guys know what a mass spectrometer is? Wait, yes?
Yeah, we learned about
It was used for isotopes, but now we're using it for compounds or fragments of compounds.
Yeah, basically you run a compound through it and it separates it and it tells you like how much percent of each thing is in the overall thing.
Okay.
And so yeah. And so the first step is we need to find the molar mass. It's always used when we need to like go from grams to moles. And then we have each atom like a specific amount of mass. And then we divide by the whole mass, which gives us a fraction of how much that actually is. And then we calculate the percent contribution. That we get is called the empirical formula. So example problem. Find empirical formula to compound that is 48.65% carbon, 8.11% hydrogen, and 43.2% oxygen. When they give us these percentages, as long as we have the correct ratio, it doesn't really matter how much of thing we say it has. So we can just say that it has 100 because it's an easy number, right? So if we have 100 grams total, this is basically 48.65 grams of carbon, 8.11 grams of hydrogen, and 43.2 grams of oxygen. And so after we have grams, we can't compare it in the formula in grams, right? So we need to compare all these moles. And so for carbon, it is 12.01. So if we multiply by 1 over 12.01, that gives us 4.05 moles carbon. Hydrogen gives us 8.03 moles of hydrogen. And 2.7 moles of oxygen. So it's down here. And so after we have all these in moles, we can compare actually how much there is. And so the way that we do this is we divide by the smallest number that we are given. So in this case, it's the oxygen, right? We have 2.7 moles of oxygen. And you know, in a formula, you can't have like less than one. We can't have less than the lowest number. So we divide the rest by oxygen. So let's start with carbon. 4.05 over 2.7 is about 1.5. And so for every mole of oxygen, we have 1.5 moles of carbon. And if we do the same thing for hydrogen, we get like 3, right? Yeah, about 3 moles of hydrogen per mole of oxygen. And so if we put these numbers in, it would be like C1.5, H3, and O1. But we can't have a fraction in the formula. So we just multiply by the number that would make the smallest number a whole number, which is 2. So that gives us C3H6O2. And that's how we go from percent mass contribution to empirical formula. Does that make sense? Any questions? No? Great. And then once we have this empirical formula, the way that we get to the molecular formula is by multiplying the empirical ratio by the actual molar mass
The empirical ratio is like the empirical subscripts, right? The subscript to the empirical.
over the empirical molar mass. That's not very legible. Yeah. So pretty easy. That's all we have for today. So you can take the rest of the time to review, or if you have questions, yes,
Zoom back in.
to the bottom part.
Yeah.
Yeah. Does anyone have any questions about this process? Yes.
Please zoom back out now.
Bless you.
There we go.
Zoom back out.
Please gather the great round of applause.
Question?
One of the practice problems earlier,
Mhm.
it was like 6 times 10 to the 20. Is that to the correct six?
This one?
Oh,
Yeah, it's just 6 because whenever we multiply, we have to do it by
no,
like
it was
something else.
the one with all the how many more ions would sample with 0.047
Yeah, and so we need to have like our lowest measure of like accuracy is what our final answer is based off on. And so in this problem, the lowest they give us is just this 2 liters. And so that's only 1/6 ring. So we can only do it to 1/6 ring. Yes.
What's the difference between the actual molar mass and the empirical molar mass?
So the actual molar mass, so the empirical molar mass is like if you did this. So like carbon's molar mass times 1.5 plus 3 times hydrogen plus 1 times oxygen. And then the actual molar mass is like this. So this is just like a ratio of 2, basically.
And the empirical ratio is just like the ratio between.
The empirical ratio is just like these numbers.
Yeah.
It's the simplest whole ratio between the atoms involved in a compound. It just gives you the right combination of one atom to another compound, but it doesn't necessarily give you the actual. Yeah.
Any other questions?
May I ask, would you like me to go through a 5-minute brief summary of the big takeaways for each section, or are you guys feeling good?
Yes.
Yeah, we'll do it. Actually, we can just
Okay, here's your quick overview from a really brave student being willing to do this for me. It was very enjoyable. And honestly, guys, if you guys have never thought about how much goes into explaining something as a teacher, and try volunteering to teach even a subsection of a class one day for your teacher that you're confident in. And it's a lot of work. So that's like big props to him. Also, big props to me. Okay. But I do this every day. Okay. Every day, 3 times in a row. And sometimes 4 if a student needs to come in during 4th and they need to walk through again. So here's the big idea. What we are moving on from is that we just talked about the mole concept and how this mole unit is one of the most important units in chemistry because it's the only unit that you can convert from one substance to another. It's also standardized. Grams are not standardized. Like 5 grams of like a leaf is not equal in amount of leaves to make that happen to 5 grams of an elephant. You cut off the pinky toe of an elephant and it's already past 5 grams, but that's 1 pinky toe. And if I was like, well, if I have 5 grams of leaf, that's like 1 leaf. No, it's not, right? So we can't trust grams. Okay, so what we do is we use the mole, and the mole allows us to explore a lot of things in chemistry, substance to substance, atom to atom, in a set ratio that's reliable. All right. So then what we moved on talking about is, well, how do we use the mole? We've already talked basic conversions between grams and particles, Avogadro's number, molar mass. Okay. But then it's like, well, how can we use it to quantify a bunch of other things, such as liquids, gases, and so forth? And we get some really cool molar values, including a molar volume value that's a set value under specific conditions, known as standard temp and pressure, STP. You will want to memorize this. 0 degrees Celsius, or when converted to Kelvin, 273.15, and 1 ATM. That's our main unit of pressure that we work in as chemists. Any gas, any 1 mole, get it, molar, any 1 mole of gas will have a 22.4 liter space occupation at STP, molar volume. That derived unit gives us an equivalence factor that we can turn into a math tool. Okay. Then you can do conversions with it. All right. You can do your standard conversions where you walk yourself through the canceling out of old units using set relationships between the eventual new units that you want, right? It's a stair-step process. Now, molar volume, what was supposed to be written here was a derivation of the math for molar volume. So let's say you were given, all right, molar mass and density. Okay. From molar mass and density of a given substance, all right, you have the derived units grams per mole all over grams per liter, which would cancel out. If you have a denominator in the denominator, it becomes the numerator, right? So it would become liters per mole. That is your molar volume unit. So you could derive molar volume for a given substance also when given the molar mass and the density. That's just kind of a sub derivation for those of you that are really into math. This isn't just some random out of the pocket unit. This is some random out of the pocket thing. We can actually get it from other measurable things, okay? Other measurable characteristics. Molarity is simply think about how much there is of it. Concentration, how much of a particle is there, okay? Higher concentration, higher molarity. We use capital M for molarity because sometimes chemists are lazy and they don't want to write moles per liter. If you write lowercase m, you are talking about something else. Okay, there's a reason we have it capitalized. It is equivalent to saying moles, little m, right, MOL, over liters. We also sometimes bracket, okay? We also sometimes bracket and say that the concentration of some compound is equal to some molarity value, okay? Some number of molarity. That's another thing that you'll see is we often use brackets to say that we want the concentration of this compound. We don't bracket the value itself. We bracket the compound we're talking about, signaling to you that we're talking about molarity. This next value is going to be molarity, okay? So, as a side note, you'll often see in the chemical write-ups that they say grab the standardized solution. A standardized solution just means we actually know the molarity, because oftentimes in labs, you'll be asked to figure out the molarity of a substance. But a standardized solution is something that's been standardized. We know it, okay? That's just like a side terminology. Then you do some math, okay? And here the idea is that you're using molarity as another step in your unit conversion stoichiometry, dimensional analysis, so forth, right? And another step in your mathematical walkthrough. Okay, so he defined. I'm gonna leave it at that. Okay. His handwriting, he told me he was gonna be legible. I guess he's decently legible. So then we go to, well, how does this connect us, this concept of mole now, to instruments that we use? So through instrumentation, right, all these theories have to have been discovered somehow experimentally. Like, you can't just pop up a theory and be like, get enough people on your side, like voting, and be like, yeah, let's go for it. Okay, and that's considered like truth in science. No, it has to be backed up by evidence. So now we're taking a look at how does the mole concept tie into the analytical instrument in the lab. So what we're doing is we're using mass spectrometry. Mass spectrometry is the process of using an instrument called a mass spectrometer that we've already seen when dealing with isotope abundance. But now we're dealing with full compounds, and we're fragmenting them and seeing how they break apart to see the various basically molar ratios that we could get between the atoms involved in the compound making. Okay, and while it would, yes, be much easier just to like look it up, people didn't have that before. People had a sample of a new compound and they're like, well, I could figure out the molar mass, but I have no idea what the formula is. I can figure out the end of giant value, but I don't know what it took to get there. So that's where empirical formula comes into place. If I can just figure out the ratio between the atoms involved, then I can figure out what I have to multiply it by to get to a mass that actually equals the actual mass that those atoms would, okay, add up to. So that's where the empirical formula comes along. And we start with something similar to composition mass, percent composition mass calculations you've learned earlier. And we assume we have 100 grams because that's just easier. Okay, we figure out the grams and we convert to moles because moles is the only way you can create a substantial comparison between the atoms. Okay, and then we divide by the smallest ratio, right? So you divide everything by 2.7. Okay, you're going to divide everything by 2.7 because you got to set one atom as the standard. If you're trying to create the simplest whole ratio number, you're trying to figure out the basic ratio between the atoms involved. So you divide everything by 2.7. The acceptable, because you're going to get some weird numbers, honestly. Nothing's going to divide perfectly. The acceptable fractions you can round up to are a half, a quarter, and a third. Those are your acceptable fractions that you round up to. Half, quarter, third. Because then you multiply out that decimal to get to the empirical formula. And then you multiply again to get to the molecular mass, depending on the ratio between the molecular mass, the actual molecular mass, and the empirical molecular mass. Okay, which he did a good job at. This was good right here. Okay, so then you get your empirical formula. And what he did is he realized, well, if it's the simplest whole ratio number, because I can't have half of a carbon, I can't just slice off carbon's head. Okay, I have to multiply by 2. Now that gives me this simplest whole number ratio between the atoms. Okay, and then we do that to figure out the actual molar mass. And then if you figured out that the actual molar mass is twice as large, let's say you figured out the actual molar mass was twice as large, okay, then your actual molecular formula would be C6H12O4, okay, as some made up compound. Is that really? Okay, yes. So that's what you guys have just learned. I have an AP problem walkthrough video that also will review some of these concepts with some practice problems. You have AP classroom quizzes tonight. You have a test tomorrow. We will start off with the MCQ online. We will get a 2-minute break and we will switch over to FRQ on paper. There are different versions. For the first test, I always give back more points. So instead of doing a 20% curve max with corrections for 10 and workbook problems for 10%, I will do corrections for 15% this time, and then an extra 10 for your workbook problems when you do all of the AP workbook problems. All right. I hopefully that covered it, reviewed it. Again, really good job. I don't know if I'll keep this video in future years, but really good job, Kevin. So good luck.